You need the notes? I think that's... You're trying to express the surface area of a sphere as a function of its volume. This one's a tough one. Anyone have a book with them? Because you might need to know these formulas. Because these are spheres, right? Would y'all like the formulas? I'll give you the formulas just to cut down on time for you. Okay? All right, so for a sphere, the surface, well, we'll do volume first. Volume is 4/3 pi r cubed. The area of a sphere is 4 pi r squared. Okay, see if you can express the surface area as a function of its volume. So you want A of V equals what? All right, we are back in business now. Just remember, if you came in a little late, I already assigned the quiz that's due next class, right? So if you weren't here when I announced that, just check with me after class. I'll tell you what the quiz is. Any other questions on this problem? All right, we're going to move on to the next set of notes. So, are there any extra notes laying around? There's some right there. Sir, did you just walk in? Did you just walk in? Okay. Thank you. So we're going to start 1.2. My goal today is to get through the first 3 sections, so let's see how this goes. We're going to talk about a catalog of functions. So these are kind of like functions you should know coming into this class. And I'm going to turn off one more set of lights so we can see this. Functions you should already have had some experience with. First of all, the power functions. I think I'll try and blow this up just a little bit. Power functions like x squared, x cubed, x to the 4th, 5th, 6th. All of these functions have 0 as an x-intercept, right? If I plug in 0, I get 0. And what else can we say? How about this one? This is like a parabola, right? Both sides go up. Cubic, what's going to change? It'll be down on the left and up on the right instead. What will x to the 4th be? No? Kind of like a parabola, except it'll be a little steeper and it'll go up a little faster here on both sides than there's the parabola next to it. The red one's the parabola, the green one's the 4th degree. Also notice this, like the parabola is above x to the 4th between 0 and 1. How about x to the 6th? Even steeper than x to the 4th. And then there's x to the 5th and x cubed. Let me take the even ones out, just look at the odd ones. So those are just your basic power functions. Negative power functions. So x to the negative 1. X to the negative 1 is the same as 1 over x. Hard to see that. Right? X to the negative 1 is the same as 1 over x. There's 1 over x. That's a rational function. X to the negative 2 is 1 over x squared. I like to call this the volcano function, right? It looks like kind of like a volcano. Both sides go up in the middle. They keep going up to infinity, though, right? What's happening at 0 for both of these functions so far? What's happening at 0? That's right. You have something, we call that a what? When a function does that at, what do we call that? You remember? Asymptote, vertical asymptote. Has a vertical asymptote at 0 because if you try plugging 0 in, it's undefined. So we have asymptote, here's x to the negative 3, which is the same as 1 over x cubed. X to the negative 4, it's like a volcano again. X to the negative 5. All of these have that weird thing happening at 0 though, right? They also have another property. What's happening to all of these functions as you go out to the right or to the left? They're all getting closer to 0, right? They're all getting closer to the x-axis. We call that a horizontal asymptote. Root functions. That's square root of x. Right, that's the function, square root of x. Kind of looks like a parabola that's been laid on its side, cut in half. How about cube root? What's going to be different when I put cube root in here? I'll have negative values because you can take cube roots of negative numbers, right? So it's going to look like that. How about a fourth root? Should I have negatives? No. So it looks very much like the square root. Fifth root, that'll have negatives. Sixth root, no negatives. All right, so that's the basic behavior of root functions. Oh, polynomials, geez. This is a huge category of functions, polynomial functions. Lines are examples of polynomials. F of x equals x. That's a line, right? What happens if I change it to f of x equals 2x? What's going to happen? Instead of x, 2 in front. What would happen to this? It'll get steeper. What happens if I change it to 10x? Steeper. Could I ever get it straight up and down? A vertical line is not a function. So it would be impossible. Okay? I guess what I'm trying to get at here is, what if the number I put in front, like right now it's 10, what if it was 100? It would be even steeper, right? What if it was 1,000? Even steeper. What if it was 1 billion? Even steeper. But you can never get it vertical. It's impossible. The bigger the number in front, the steeper it gets, but you just approach vertical, but you never get there. All right? Now that's just a line. That's an example of a polynomial. This is what we call a degree 1 polynomial because the power on the x is 1. Now what if I make the number in front here a negative number? What's going to happen? It's going to slope the other way, right? And then again, negative 2, negative 3, negative 4. The bigger I get negative, the steeper it gets that direction. But I can never get vertical. So those were lines. All lines are examples of polynomials. Now what if I make it instead of a degree 1, and so instead of x, I make it x squared. Now it's a parabola, isn't it? And I could have parabolas that look like that. Maybe I could do something like this. So now I have two x-intercepts, 0 and 3. I can flip it over by changing the number in front of the x squared, making it negative. Now it opens down, right? So quadratic functions, parabolas, are examples of polynomials. But you can keep going, right? Polynomials, you can go higher and higher degrees. There's a 3rd degree polynomial. Changing the scale on the graph so you can see that a little better. I can do separate x-intercepts there. That's 3rd degree. I can change the numbers to make it flip the other direction. These are all college algebra topics, polynomial functions. The thing about polynomials, though, is they're always nice and smooth, aren't they? Like, there's no like crazy breaks in the graph. And for degree 2 and higher, they're always curved. Like lines are just lines, right? But from degree 2 and on, you get curves. Watch, I'll go a degree 6 polynomial here, and I'll throw in a bunch of different roots. Let me do one more here. Let me scale this out so we can see it. See if I can get this to come in. I may not be able to get it all in here. Not quite. Can't get it all in there. But it goes down, then it comes up, and then it comes back down and up, and then back down, and then back up. Right? So everyone's comfortable at least with the idea of what polynomials look like. Rational functions. Again, rational functions are a college algebra topic. Rational functions are defined to be a polynomial divided by a polynomial. So if you divide two polynomials, you get a rational function. And they have these things called vertical asymptotes, where the function takes off, gets all crazy. This is another thing you can play with here. Change the degrees, change different values. This is the function right here. It's graphing. Okay, so rational functions usually have vertical asymptotes and horizontal asymptotes. We're not going to do a full-blown study of these, just as long as you've seen them, good. Trig functions, that is the classic sine function right there, right? Cosine, looks like that. Tangent, what does tangent have that sine and cosine don't have? Has asymptotes. Does anyone know where the asymptotes for tangent are? Yep, it goes, there's like this vertical, where is it though? Does anyone remember? There's two like classic ones everyone should remember. Pi over 2 and negative pi over 2, good. There's tangent, the blue. Let me take sine and cosine out of here. Hey, what is tangent? In terms of sine and cosine, what's tangent? Sine over cosine, right? So if tangent is sine over cosine, then every time cosine is 0, shouldn't you have something division by 0? Every time cosine is 0, shouldn't you have division by 0 for tangent? Do I need to write that down? Here's what I'm trying to say. If tangent x is sine x, over cosine x, then whenever cosine is 0, you should have division by 0, right? Which should cause a problem, shouldn't it? So let me go back to that graph, and let me bring cosine in here. Look at where cosine is 0. Look at where cosine is 0, right here, right? And what's happening to my blue function at that point? I have my asymptote. And every time cosine hits 0 again, that's where I create asymptotes for the tangent function. Yes? So then what about cosecant then? What is cosecant by definition? 1 over sine. So where should cosecant go crazy? Wherever sine is 0, which would be, here's sine. I put sine back up here for you. Where is it going? Where is sine 0? 0, pi, 2 pi. So if I pop cosecant in here, shouldn't I have asymptotes there? And then this is cosecant up here. Cosecant, cosecant, that part. Do I remember graphing cosecant and secant and stuff in pre-cal? It's been probably forever, but okay, what about secant? Secant we said was 1 over cosine. So let me take sine out of there and put cosine back in. Let me throw secant in there. I should have problems wherever cosine crosses the x-axis. Take cosecant out. So there it is. Wherever cosine crosses the x-axis, I have an asymptote. So it's this black function right here. Last one, cotangent. What's cotangent by definition? 1 over tangent, but in terms of sine and cosine, what is it? Cosine over sine. So everywhere sine is 0, so let me put sine, I should have a problem. So here's cotangent. So again, sine is 0 here, I have a vertical. Sine 0 here, I have vertical. Take that out, that's your cotangent. Okay. Remember, these go on, right? These repeat. It's like any of these, you could put them up there, and they just, the periods, they just keep